All right, well, we can probably get started now. People are going to continue to come in. We did pick dinner time, so I'll start with some introductory remarks and then Dario will give his presentation. So welcome everyone. Thanks for joining us for another Roebling road trip. And a big thank you to everyone who made a donation. Our programs have been pay what you wish during the pandemic in order to support our community, and every donation of any amount helps our museum run programs like this, as well as to continue to collect and preserve Roebling's history. So for those of you who haven't met me yet, it says on my my screen that my name is Roebling Museum. That's not true. I'm Lynn Calamia. I'm the new executive director at Roebling Museum. I started right before the pandemic hit, so it's been, what, 2 years now? But I'm still gonna say new because I haven't met you guys all in person yet, and I hope we can start doing that more soon. And for those of you who haven't visited yet, Roebling Museum, we are actually back open 3 days a week, Thursday, Friday, Saturday. And we are located, our museum is located in the former company town of Roebling, New Jersey, which is located in central New Jersey, right on the Delaware River. Our company town is listed on the National Register. It was built in 1905, and it remains almost fully intact architecturally. So I usually say it's about 98%. One building burned down and another one was moved, but it still exists. So I think 98 sounds like the right number. But our museum, it's actually located on the site of the former Roebling Company wire rope factory and steel mill that produced the materials needed to build some of the most iconic suspension bridges in the United States. We have both indoor and outdoor exhibits, and they bring to life the story of the people who lived in the company town, as well as the big impact that the Roebling Company has had overall. So today, we're going to go on a Roebling road trip. And for those of you who haven't tuned in before, definitely recommend that you check out our YouTube. All of our programs are recorded and they do appear on our YouTube channel once I edit them. So keep an eye out. It usually takes about a week for me to get those up there. But Roebling Road Trip, as a program, we try to take our viewers, our visitors around the country to visit with people at other Roebling related sites. So far we've been to a big bridge in Cincinnati, the Allegheny Portage Railroad, the town founded by John Roebling, of course, the Brooklyn Bridge. And we'd really love to hear what you'd like to see next. So send me an email or submit them in the Q&A or chat box as we go, and I'll keep an eye out. So, and this is, you've heard it here first. We have a couple more programs actually booked, but they haven't been announced yet. So the next one is going to be on Emily Roebling. And the one after that is going to be about the World's Fair. And then there's another one that will be about a small footbridge in, I want to say it's in Maine, but it could be in Vermont. You'll just have to tune in to find out because I don't remember off the top of my head, but it'll be good. So how this program is going to run tonight. Our guest, Dario, who you can see in his little box up here, he'll give an illustrated lecture. And while he's talking, you please do submit questions as they occur to you. If you see something that's interesting and you want to ask a question, type it in the box because I'll be monitoring the Q&A area. So once he's finished talking, I'll start asking those questions to him so that we can get a conversation going. Right, well, I don't want to take up any more time talking, so without further ado, let's get started. Are you ready, Dario?
Yes, I am. Thank you, Lynn. Can anyone see my screen? Huh? Good. Well, hello, everyone, and welcome to this Roebling Museum road trip. This evening, I'll be speaking on the engineer Charles Cecil Sunderland of the John A. Roebling Sons Company. I think we're all familiar with the great accomplishment of the patriarch, John Roebling, and his legacy was, of course, continued by Washington Roebling and his wife, Emily, who completed the firm's great work in 1883. Ferdinand managed finances while Charles focused on improving production technologies. However, by the end of 1918, both Ferdinand and Charles had died, and Washington was over 80 years old. Engineering leadership had to be provided by others. And preeminent among these other engineers was Charles C. Sunderland. Sunderland was born in 1881 near Halifax, England. He immigrated to the US as a 9-year-old boy in 1891. The family settled in Esopus on the Hudson River, about 75 miles north of the city. None of his employment records and other papers I examined noted his education. His granddaughter, Kathy Whitkay, also does not have any information on his education. So it is probable that he was largely self-educated. Employment records show that Sunderland was hired as a draftsman at Roebling's on October 15, 1901, just a few days before his 20th birthday. In 1905, his title was that of assistant engineer in the bridge and tramway department. By 1910, at age 29, he was engineer in charge of the wire rope division, surely one of the most important engineering positions at Roebling's. In 1929, he was made chief engineer of the newly formed bridge department, a position that he held until his retirement on May 15, 1952, after 50 years and 7 months of continuous service. This brief talk will describe how over the decades, as he advanced leadership positions, Sunderland really sustained Roebling's engineering and manufacturing vitality by fostering research, developing new technologies, and manufacturing very high quality products. However, I regret that I don't know anything about Sunderland's engineering activities from 1910 to about 1926. I don't know his contributions to Roebling's World War I production, nor his contributions to Roebling's unsuccessful bid for the Benjamin Franklin Bridge cables in 1922. I don't know what improvements he made to Roebling's 80-ton rope-making machine, and I don't know any improvements that he made to Roebling wire rope designs. But as engineer in charge of the wire rope division, he must have worked very closely with Charles Roebling and must have made significant contributions that merited his promotion to chief engineer of bridges. Wire ropes were, of course, John Roebling's original development and clearly remain Jarsker's signature product. The basic component of wire rope is high-strength steel wire. Wires are then helically wound to make strands, which in turn are used to make wire rope, a very highly engineered product. This is a patent that for a specific type of wire rope filed in 1915, late in Charles Roebling's life, and only granted in the year of his death in 1918. Roebling's 80-ton wire rope machine has, of course, been designated a historic mechanical engineering landmark by the American Society of Mechanical Engineers. In 1926, the year Washington Roebling died, the design of the George Washington Bridge over the Hudson River in New York City was being finalized. The principal design engineers were Othmar Ammann, the chief engineer of the Port of New York Authority, Leon Moiseyev, advisory engineer on design for the Port Authority, and Alston Dana, appointed as engineer of design in charge of the design division. He had a staff of over 30 engineers and draftsmen working under him. Both Dana and Moiseyev had previous experience in suspension bridge design, but this was Ammann's first suspension bridge. The final design had a main span of 3,500 feet and an upper deck with 7 traffic lanes. A second deck was added only later and did not have the 4 projected railroad lines. There were 4 main suspension cables, and each cable was 36 inches in diameter. Charles Sunderland was responsible for preparing Roebling's bid for supplying the wire and anchorage steel and for erecting the cables of the George Washington Bridge. Roebling won the contract with a bid of $12.2 million, which was about 40% of the total cost of the bridge proper. Sunderland was appointed Roebling's chief engineer for the execution of the George Washington Bridge contract. The scale of the work that Roebling had to complete was unprecedented and daunting. This is a table prepared by Sunderland that compares the 6 largest existing suspension bridges with the George Washington Bridge. The most striking fact is that the George Washington Bridge was designed to have a main span of 3,500 feet, twice as long as the previous longest span, that of the Delaware River or Benjamin Franklin Bridge in Philadelphia. The total weight of the wires of the main cables of the George Washington Bridge was 28,500 tons, greater than the combined weight of all of the cables of the 6 largest suspension bridges built to date. The suspender ropes had the largest diameter ever used in a suspension bridge. The ropes were sophisticated assemblies. The 2 7/8" diameter ropes had 283 wires of 10 different sizes. Wire ropes have an irreversible stretch from compaction when an applied load exceeds the tension used during manufacturing. This makes the elongations and the lengths of ropes under service forces uncertain. To eliminate this uncertainty, Sunderland designed and built a unique machine at Roebling's CONCORA plant. The machine, now called a prestretcher, consisted of an 1,875-foot long bed along the Delaware River with a 300-ton wheelie hydraulic testing machine at one end to measure force, and hydraulic cylinders with 5.5-foot strokes at the other end to apply the stretch. In effect, it was basically an 1,875-foot long testing machine to measure elongations of cables with known applied forces. Typically, forces equal to 125% of their expected service load were applied. The moving end was a large sheave or pulley on a track so that ropes as long as 3,750 feet could be pre-stretched. The operation of the pre-stretcher was very precise. A rope was stretched several times. One stretch was typically maintained overnight for over 10 hours, and length measurements were taken before sunrise to avoid temperature effects. The machine provided data from which tension versus elongation plots could be drawn. These tension versus elongation plots are unique. They never before had been obtained for such long wire ropes. Two very important observations are that the rope stiffness, or the tension required to cause a given elongation, increases dramatically after the first stretch, and the stiffness after the first stretch remains constant. Therefore, the lengths of pre-stretched ropes in use could be precisely calculated. I just want you to note something, that when a force of 205,000 pounds was applied, a 100-inch length of rope initially stretched 0.385 inches, which meant that an 1,875-foot long rope stretched over 7 feet. Therefore, since the jack stroke was only 5.5 feet, the pre-stretching operation had to be done in stages of gripping, stretching, transferring the load, resetting the jack, re-gripping, and more stretching. The operation of the pre-stretcher required a careful sequence of potentially dangerous steps. The CONCORA pre-stretcher really revolutionized production of long ropes and was copied by competitors. These are some photos taken by the historic American engineering record and by Don Sayenga, the noted historian of wire ropes. Although I have not personally seen them, significant components of the CONCORA pre-stretcher seem to be extant. In my judgment, the CONCORA pre-stretcher merits conservation and designation as a historic mechanical engineering landmark. However, the pre-stretcher measured only stiffness, not strength. The strength of the large diameter ropes was unknown and could not be determined with any available testing equipment. Therefore, Sunderland commissioned a testing machine that could apply 2.5 million pounds of force, greater than the capacity of any other available machine. It's amusing to really read test accounts, which describe the anxiety at hearing the first wire failure and the report and building vibrations produced when a wire rope finally broke. Building a bed that could pre-stretch a 3,750-foot long rope was necessary because the ropes were first used to support footbridges, which were about 3,560 feet long. Therefore, the length of the George Washington Bridge footbridges determined the length of the CONCORA pre-stretcher. The ropes are shown in the highlight area on the left figure. The drawing on the right shows a completed cable, fully assembled main suspension cable, and a partial cable during assembly. Each circle represents a strand, or in a bundle of 434 ropes, or wires rather. The strands are arranged in a hexagonal shape with one of the sides of the hexagon in the horizontal position. Long wire lengths were obtained by splicing. Sunderland carried out rigorous testing to verify the capacity of wire splices. Almost 12,000 tests of splices were performed, which indicated that they on average developed 98% of the strength of the wire. Splices were made by deforming the ends of the wires and then pressing on or swaging 2.5-inch long sleeves. A quick, elegant, effective process defined by Roebling. The suspension cable erection process, although it still used the spinning wheels conceived by John Roebling, was much more sophisticated in its control and rate of placement. Sunderland wrote chapter 24 of Schuyler's 1931 book on the Roeblings and listed 16 features that were developed specifically for the George Washington Bridge. Sunderland stated that they were, quote, the result of 2 years scientific and mechanical investigation in the laboratories of the Roebling Company, unquote. After 434 wires were spun, they were combined into a strand, and each strand was precisely placed within a hexagonal pattern over the saddles. After all 61 strands for the cable were assembled, the cable was compacted into a circular shape and then wrapped with wire, just as John Roebling did in 1845. The weight of the footbridges was then transferred to the main cables, and the wire ropes that supported the footbridges were repurposed to serve as the suspenders for the deck. Note that because of the known stiffness of the pre-stretched ropes, they could be cut to precise lengths, and simple, elegant, swaged connections could be used to support the floor girders. Adjustable turnbuckles were not needed. Sunderland and his staff of Roebling engineers and iron workers achieved what was thought to be impossible. Sunderland succinctly observed that the first set of cables was finished over 1 month ahead of contract, and at the same time, the second set was completed, 13 months ahead of contract requirements. Roebling positioned 56.6 million pounds of bridge wire in about 10 months. With Sunderland's leadership, the Roebling Company achievement allowed the opening of the George Washington Bridge 8 months ahead of original schedule. Othmar Ammann, the chief engineer of the Port Authority of New York, wrote a letter to Sunderland stating his appreciation. It reads in part, I'll read it for you. I take the occasion to express to you on behalf of the engineering staff of the Port Authority its appreciation of the excellent and efficient manner in which you have carried out this unusual and important work, and in particular also the cooperation which you and your engineering staff have manifested throughout the period of construction. This was truly effusive praise from the very reserved Swiss Ammann. On the group photo of the Roebling staff shown at left, Sunderland is barely visible, standing next to the Roebling superintendent, Howard Hills. The availability of Sunderland's prestretcher at CONCORA had an immediate effect on the design of medium-span suspension bridges. The eminent bridge engineer David Steinman designed 2 medium-span bridges at the time the George Washington Bridge was being erected, the Grand Mare Bridge in Quebec and the St. John's Bridge in Oregon. Steinman realized that Roebling's ability to fabricate very long lengths of strand to a very precise length tolerance meant the main suspension cables could be formed by simply bundling pre-cut, pre-socketed Roebling strands, precluding the need for cable spinning. For the Grand Mare Bridge, Steinman used 37 pre-stretched, shop-socketed Roebling bridge strands. Each 1,680-foot strand had to meet a length tolerance of plus or minus a half an inch. For the St. John's Bridge, Steinman used 91 bridge strands. Each 2,720-foot long strand had to meet a length tolerance of plus or minus 1 inch. Imagine building something that's 2,720 feet long to plus or minus 1 inch. It's impossible. By the early 1930s, the Roebling Company not only manufactured unique wire ropes, strands, and end connections, but they also had the engineering and construction expertise to design and erect suspension bridges. However, Roebling leadership evidently elected not to compete with U.S. consulting engineers for U.S. commissions. because the consulting engineers were also potential customers for Roebling's manufactured products. Roebling did compete for commissions outside the US. One example is the San Rafael Bridge in the Dominican Republic. This bridge was designed and completely prefabricated in Trenton, New Jersey, and then erected by the Roebling Company under direct contract with the Dominican government. Sunderland used 9 pre-stretched, pre-socketed bridge strands, but he did not bundle them and wrap them with wire like John Roebling did. Rather, he decided to leave them in an open, parallel arrangement, relying on the galvanizing of the individual wires for corrosion protection. Sunderland espoused this philosophy for subsequent medium-span suspension and other types of bridges. Trenton, of course, is close to Princeton, New Jersey. This proximity naturally led to collaborations between Roebling engineers and structural engineering students and professors at Princeton. In 1930, at the time of the erection of the George Washington Bridge, a conference was held at Princeton to determine if physical models could be used for final design of a suspension bridge. It was attended by practically all the prominent US suspension bridge designers whom I've highlighted. As usual, most of the work was done by a bright undergraduate student named Blair Birdsall under the direction of Professor George Beggs. In a photo, Charles Sunderland is in the front row, second from left. Birdsall is on the last row, third from left. Amann also attended the conference, but as a Swiss, he chose not to be in a group photo. So I've added his image on the right-hand side. There's Amann here. The main result was that from the experimental work was that it was feasible to use physical models to fully design a suspension bridge. But most importantly, Blair Birdsall joined the Roebling Company in 1934, bringing expertise and a disposition toward the use of physical models for design of innovative systems. Over an 18-year collaboration, Sunderland and Birdsall truly bonded as mentor and protege. It was Birdsall's great, extreme good fortune that Roebling won the contract to supply the wire and erect the main cables for the fabled Golden Gate Bridge, and that he was assigned to work on the erection of the cables. Blair Birdsall noted that in preparation for work on the Golden Gate Bridge, Sunderland developed a much improved scheme for cable construction. This drawing compares the cable construction of the saddles of the George Washington Bridge. For the George Washington Bridge, Sunderland used uniformly sized strands with 434 wires layered horizontally with a hexagon side at the base of the saddle. For the Golden Gate Bridge, Sunderland used strands of sizes varying from 256 wires to 472 wires. He stacked the strands vertically in vertical columns with a hexagon apex at the base. The Golden Gate arrangement had two important advantages. Vertical stacking made the temperature of the strands much more uniform along the span. And both the vertical arrangement and the variation in strand size allowed a much more efficient compaction of the cable. The George Washington Bridge cables have 22% voids, whereas the Golden Gate Bridge cables have only 17% voids. These advantages were significant, and the technology diffused internationally. Here are statements from two late 20th century prominent British and Japanese suspension bridge designers. All the major British suspension bridges have main cables that are of the built-in in situ parallel type pioneered in the USA by John A. Roebling, with the strands in a vertical rather than horizontal form. Dr. William C. Brown, Freeman Fox and Partners. Because of the good experience with Roebling's strand arrangement on the Kunmon Bridge, all the cable arrangements for the Honshi Bridge project were designed with a vertical hexagon apex. Ichiro Konishi. Most recently, the Çanakkale Bridge over the Dardanelles Strait in Turkey was formally dedicated about 3 weeks ago. It has a main span of 6,635 feet, the longest in the world. At the left is a photo of the towers, and at right is a screenshot, I should say, of the saddle. Note the pattern of blue slots for positioning the strands. It's exactly the same as that pioneered by Charles Sunderland for the Golden Gate Bridge over 85 years ago. But after the euphoria of the great design and construction successes of the George Washington and Golden Gate bridges, American engineers received a blunt lesson. The Tacoma Narrows Bridge collapsed in a windstorm on November 7, 1940. The film of Galloping Gertie tearing itself apart has been seen by practically everyone. The failure occurred because design engineers did not understand the dynamic forces caused by wind, nor how to design a deck to limit dynamic responses. Of course, several investigative bodies were formed. The most prominent was convened by the American Institute of Steel Construction and the Public Roads Administration. Sunderland and Birdsall were members, and the Roebling Company heavily subsidized the cost of board activities. But after December 7th, 1941, the nation was really focused on the war effort. In June 1944, Roebling received a contract from the US Army to design a suspension bridge of 600-foot span that could carry Army tanks. Because of the collapse of the Tacoma Narrows Bridge, Sunderland had already considered alternate ways of stiffening suspension bridges and had conceptualized a new form called the cable truss. The system devised by Sunderland did not rely on the bridge deck to augment the stiffness of a suspension bridge. Rather, it was a truss-like system, but with all cable tension members. Its stiffness was increased by tensioning the bottom cord, which increased the tensile forces in the members and thus their stiffness. However, Sunderland's cable truss was very difficult to analyze mathematically. Therefore, Birdsall and Sunderland built a 1/10 scale model and predicted the behavior and designed the bridge based on the behavior of this model. The image of the left shows model vehicles, presumably tanks or models of tanks, traversing the model bridge. Because the war ended before the research was completed, the US Army canceled the contract and full-scale prototype bridge was never built in the United States. This is a post-war Roebling publicity photo showing Birdsall on the left and Sunderland on the right, pretending to be taking readings from a cable truss model. In 1948, the Roebling Company won a contract to design and build a bridge over the Rio Lempa near the town of San Marcos in El Salvador. Sunderland and Birdsall decided to design, fabricate, and erect their first cable truss bridge. It was a 5-span bridge with a total length of 2,550 feet. The deck and longitudinal girder were very slender because they were not designed to increase stiffness. The bridge was completely prefabricated in Trenton and shipped to El Salvador. Following Sunderland's philosophy, the top cord consisted of an open array of pre-stretched, pre-socketed galvanized bridge strands. The lower cord was also an open array of 8 strands, pre-tensioned to produce tension in the diagonals. The right-hand drawing shows that the tension in the lower cord strands was equilibrated by placing the concrete deck in compression, an ingenious solution without precedent. The San Marcos Bridge was certainly one of the most innovative bridges built in the mid-20th century. It was uniquely a Roebling achievement, with a design based on their experimental research, with Roebling wire strands and end connections, and with many unique Roebling steel forgings and castings. No other manufacturer or consulting engineering firm in the world had the breadth of engineering knowledge, manufacturing capabilities, and construction expertise to conceive and execute such a design. But Sunderland always prioritized the Roebling Company as a manufacturer, financially dependent on selling wire, which meant anticipating and creating markets for their products. Therefore, in 1944, Sunderland also began research on pre-stressed concrete and later collaborated with Rio Paz, a British engineer who had emigrated to the United States. This technology was pioneered in Europe, and the Europeans were ahead in this kind of technology. But Sunderland knew that his products were as good as any high-strength European product. Moreover, Roebling had unique experience with pre-stressing steel structures. Therefore, following Sunderland's and Birdsall's traditional research methodology, they began by building a model structure. It was a 20-foot long model, proportioned to be a 1/10 scale model of a 200-foot long bridge. The model consisted of 5 4-foot long precast concrete sections post-tensioned together with 10 parabolic galvanized aircraft cables. The model was similar to beams proposed by 2 German researchers, Dischinger and Finsterwalder. But Sunderland had a precise objective. They sought to determine if time-dependent strains in the concrete caused significant losses in the pre-stress forces and large increases in displacements under a constant load. Measurements over 3 years indicated that a permanent state of pre-stress can be achieved with no measurable increases in displacements after the first year. With knowledge of such positive experimental results, Sunderland began using post-tension modular concrete floors on Roebling design bridges. The floor of Roebling's extant Lumberville pedestrian bridge over the Delaware River was precast using 4-foot by 9-foot modules. This was a very small job, but it was surely done as a marketing demonstration of the potential of pre-stressed concrete and the usefulness of Roebling products. Another bridge designed, fabricated, and erected by Roebling was the Rio Paz suspension bridge between Guatemala and El Salvador, completed in 1949. The Sunderland type main cable, consisting of an open array of bridge strands, the bolted plates for connecting the suspenders, the socketed suspenders are all distinctly Roebling features. The floor of the bridge was precast using 21-inch by 21 feet, 7-inch modules. The modules were then post-tensioned along their length and then post-tensioned longitudinally. The Rio Paz bridge is extant, but I don't know whether the deck is still the original one. The first great opportunity for Roebling to showcase its capabilities in pre-stressed concrete in the United States came from the city of Philadelphia, downriver from Trenton. The city needed to replace a bridge to carry Walnut Lane over Lincoln Drive and Monoshamy Creek. After 2 bids exceeded the budget, the city in 1947 indicated a willingness to consider pre-stressed concrete bridge proposals. The first proposal for a pre-stressed concrete bridge on Walnut Lane in Philadelphia was made by Leo Koff, Charles Sunderland, and the John A. Roebling Sons Company. This is a rendering of the Koff Sunderland Roebling proposal, which featured haunched continuous girders. Some structural details are given by these drawings. There are 3 box girders and continuous draped pre-stressing ropes. It is an astonishingly advanced design that would be considered modern if built today. It features all of the Sunderland principles: post-tensioning, torsionally stiff box girders, large galvanized tendons, continuous tendons, unbonded tendons accessible for inspection, and compact swaged anchorages. Regrettably, the Koff Sunderland Roebling design was too advanced. The city of Philadelphia chose the design of Professor Gustav, a well-known Belgian pioneer of pre-stressed concrete, who had made a later proposal in April 1848. Manuel, in fact, chose to use Roebling's high-strength, ungalvanized cold-drawn wire for the Walnut Lane Bridge, which was arguably better than any European product. Manuel's Walnut Lane Bridge opened to traffic on February 1st, 1951, and is traditionally considered the first pre-stressed concrete bridge in the United States. Despite Sunderland's disappointment, Roebling's post-tensioning systems inspired several other pioneers of pre-stressed concrete. Ross Bryan in Tennessee and C.L. Johnson in Michigan built block bridges using Roebling post-tensioning products. These early bridges were built at the same time as the Walnut Lane Bridge, but received much less publicity and recognition. The real fruition of Sunderland's vision of post-tension concrete bridges with unbonded, galvanized, accessible tendons was realized not in the US, but abroad in Cuba, shortly after his retirement in May 1952. 5 post-tension bridges were designed and built in Cuba using Roebling post-tensioning technology in collaboration with Luis Sáenz, Mario Suarez, and Jose Marti. They are the Canas, Agabama, Arimao, Cuyagateje, and Felipe Pazos bridges built from 1952 to 1956. The Cuyagateje Bridge had a main span of 300 feet with a variable box girder depth, which improved both the appearance and the structural efficiency. In summary, Charles Sunderland, the John A. Roebling Sons Company, together with consulting engineer Leo Koff, developed a complete American concrete post-tensioning technology from 1944 to 1952. These included high-strength, large-diameter, galvanized and pre-stretched strands and ropes, compact swage anchorage systems, and box girder bridge designs with accessible, unbonded, large-diameter, continuous tendons. The extant post-tension bridges in Cuba are a strong vindication of the Sunderland Roebling Koff approach or philosophy of corrosion protection. Sunderland's legacy is perhaps best appreciated by his peers. These are a few testimonials to his character, vision, and engineering contributions. On main cables and suspension bridges. In preparation for work of the Golden Gate Bridge, Charles C. Sunderland developed a much improved scheme for cable construction. The genius of the man responsible for the cable of the longest spans in the world, Leo Koff, on cable truss suspension bridges. The main features of the superstructure design were conceived and developed by the late C.C. Sunderland. The El Salvador Bridge is a memorial to his vision and genius. On pre-stressed and post-tension concrete, it is understandable that the great Charles C. Sunderland would follow the example set by the Roeblings, Charles Zollman. Thanks to the vision of Mr. Sunderland, we started development work on adapting the principles of pre-stressed concrete to American practice in 1944. And by the time these principles became sufficiently recognized in this country to begin produce a market for wire, we were thoroughly entrenched as one of the recognized authorities in the field, Blair Birdsall. Our only regret is that one of the grand pioneers, our former chief at the Roebling Company, boss Sonny Sunderland, cannot be present to view with satisfaction the fruits of his vision. Thank you very much. Thank you, Lynn.
Wow, that was so good. I was taking notes that whole time. And I'm so glad to hear that his nickname was Sonny Sunderland.
I wanted to
adorable.
emphasize that. I wanted to emphasize that.
That's fantastic. Yeah, I think one of the things that I deal with a lot, I've been giving tours at the museum and doing my own research, and we talk a lot about how the Roeblings built bridges, and your talk really sort of gets at that question of like, what does it mean to build a bridge? Because they did so many different parts of building. They did engineering, they did the materials, and even the pre-stressed concrete ones, which is not normally what you think of when you hear Roebling. You think of like suspension kind of stuff. They were involved with that too. It's really amazing.
It is. It was a unique firm that had manufacturing capability, engineering capability, as well as erection capability, construction capability. By the way, they lost their shirts on a bridge in El Salvador. They lost about $700,000 on that job.
Well, they can't all be successful. All right, so we do have some questions that have come in while you were talking. Let's start with, this is a general question, which I think I personally would love to hear more about. Can you explain more about the tension on the wire rope? I didn't get all the explanation and I really want to understand it.
At the pre-stretcher level?
Yeah, this came in while you were talking about the machinery that we still have at Roebling.
Oops, sorry. So this was this pre-stretcher. It was an 1800. Is this, am I addressing a question, Lynn?
Yeah, about the tension on the wire rope. How did they put it on the rope and why did they put it there?
Okay. They pre-tensioned the rope with jacks. One end was fixed. The end that had the testing machine. The other end had hydraulic cylinders, and these cylinders retracted. And as the cylinders retracted, they put the rope in tension. The reason they did this is wire rope, when you make it, the wires are relatively loose. So when you stretch it, they compact, and therefore the stiffness is much smaller when they compact. So you have to, and you don't know the length of these ropes if you want to use them in an application. So by pre-stretching, they eliminated this irreversible stretch from compaction, and they created a product that had consistent stiffness and known length. So the pre-stretcher produced a product that had a consistent length and a consistent stiffness. I don't know if that explained things. Well,
yeah, but also building off of that, there's another question that came in from actually one of our docents at the museum. And she says that as a docent at the museum, what would you say is the best way to describe what the pre-stretcher did to visitors, assuming they haven't seen this lecture? And I think she didn't write it here, but I know that I've heard in the past some of the folks in our museum describing it like a t-shirt that's pre-shrunken. So the people who buy it, it's already shrunk as much as it's going to shrink. So you're ready. You're not going to get any surprises. Is that not inaccurate?
No, that's a valid analogy in reverse. So a t-shirt shrinks and a cable really expands, or as you pull it, there's an irreversible stretch that occurs. In other words, if something was a foot long, you would stretch it and it would keep that stretch, but for the first time. But after the first time, any additional stretch that you put on it would go back to the original length. So it's a reverse of that kind of a shrinkage process for a t-shirt. I would have to think about this, and maybe I'll give you a better analogy for you to give to your visitors. Would that be okay?
We would love that, because one of the other questions that's coming in is what is left of the buildings and the machinery on site. And I can speak to this a little bit because I've seen them, and these are really good pictures. We affectionately refer to them as buildings 92 and 93, but they are the two pre-stretcher buildings, and they are in place right now where they were. But we believe the EPA has some plans to maybe get rid of them or take them off of that location and move the actual machinery. So if you do come to the museum, there's this the Delaware River Heritage Trail that goes along the Delaware River, and you can walk right up next to the two buildings. And you can even, I was talking to Dario about this earlier this week. The buildings they like reflect the length of the wire, and the distance between the two buildings and the pieces of the machinery really tell the story of how long the cables really were at the time. So I definitely recommend coming to the museum, but I also recommend taking a walk on the river trail. You can't get into the buildings, but you can definitely see them and get pretty close.
I definitely think that the length, which was determined by the length of the footbridges on the George Washington Bridge, is an inherent aspect of the machine. It's the scale and the length of the machine that really defines a machine.
Agreed. Okay. This is from a gentleman named Tom. My father, Tom Pearson, was a supervisor and lead foreman at the Prestressed. Hello. I'm going to need to talk to Tom from the 1960s to about 1973. And he was called in on second or third shift, where he would talk about equipment problems, not wire rope problems. Do you know of any typical problems that would happen with the equipment rather than the rope?
I regret that I do not. I regret that I do not. But I would love to speak to this gentleman, especially if he has any anecdotes from his father regarding the operation of the machine. I think I still have some things to learn about the operation of the machine, and I would love to speak to him. But I don't know about which problems arose as you were stretching.
That's great, though. We should have a special meeting with Tom Pearson and do an oral history about what he remembers from.
I think that's a good idea.
Okay, what else? Why did they lose so much on the El Salvador Bridge?
Because they really had construction problems. They had floods. They had to utilize local labor, which was untrained or not experienced with suspension bridge erection. So both because of flooding of the Rio Lempa and inexperienced labor, I would say, those were the two main reasons. There's nothing wrong with the design. I don't know if you caught it on the slide that I showed, but another tragic thing happened. It was destroyed by guerrillas in a civil war in 1982. So
Wow.
they blew up the entire bridge. So it doesn't exist anymore as a bridge. So this was unique in the world. So something that was so uniquely Roebling was destroyed in a civil war in 1982.
Wow, that's really amazing. All right, we do have a question about the while we're talking about specific bridges, isn't the Lumberville Bridge an experiment in a cable stiffened bridge,
Yes,
as well as a prestressed concrete deck?
Correct. I see. I sense an engineer in the audience. Huh?
It's very easy to sense them. Okay, we do have another one here.
I can answer if you.
Yep.
Yes.
Okay. Yeah.
Yes.
Go.
I had. So yes, it was both an experiment in pre-tensioning of cables, as well as post-tensioning concrete. It was kind of a precursor to the San Marcos Bridge. So this design was refined, really, that led eventually to the San Marcos Bridge. But you're right, it was a pre-stressed suspension structure, both in steel and in concrete. So again, this was only achievable by Roebling. This bridge, I mean, this deck does not exist anymore. It was replaced by PennDOT with something else. But the original deck was a demonstration of post-tension concrete, and the Lumberville Bridge is a demonstration of pre-stressed cable stiffened structure, suspension bridge.
Sounds like that one's not too far away from the museum. I might have to go visit. Okay, another question. Excellent talk, Dario. I hope you turn it into an article or book. You do have an article about this, right?
I have two separate articles that appeared in conferences, yes, and they both are available as PDF files. And then, as you know, I have a YouTube video that is I modify this talk, but the YouTube video has essentially many of the same points. So you can look at the YouTube video and go over the talk again.
Okay, well, that's not actually his question. His question is, can you talk a little bit about the small 1943 cable truss bridge that still exists at the Roebling Trenton plant?
I detect Stephen Buonapane here, huh?
Close, Clifford Zink.
Oh, Clifford Fink?
Zink, yeah.
That was also an experiment to, there were basically two ways to stiffen before the development by Charles Sunderland of a cable truss. There were two ways of building a suspension structure. One was to provide stiffness by making a stiff deck, and the other one was to provide stiffness by stiffening the actual pair of suspension cables that suspended the walk structure. So that kind of a design had been used before. There were many designs that utilize a so-called stiff cable design for suspension bridges. There was one built in Pittsburgh, one in St. Louis. So there was nothing really exceptional about that design, except that it did not need a stiff deck. The deck could be very, very slender, and all of the stiffness was provided by the fact that you made a truss or an inverted arch, basically, out of the suspension cables, Clifford. Does that answer your question?
It seems like it does.
Okay.
Let's see. Here's a question that I've had. If you stretch the wire too much, does it snap? Have they found a way to prevent the snapping?
No, that's the nature of wire. Nothing is more dangerous than a wire breaking or a rope breaking. It is an occurrence that occurs sometimes in post-tension concrete in the United States. And when this happens, everybody there's a danger of death and severe damage. So if one of these pre-stretcher ropes broke, that would have been simply catastrophic. It would have caused incredible amount of damage. So because of the energy stored in the rope, so you're stretching like a rubber band, but you're stretching a huge rope. So you're storing much, much more energy in a rubber band. So if a rubber band breaks, it hurts your fingers. If the rope broke, it would have taken down the both buildings. It would have taken down, leveled both buildings. The force that was used to pre-tension the ropes was way less than the capacity of the rope. So they typically use 300 tons, which is 600,000 pounds. And the capacity of those ropes was at least twice that, 1.3 million pounds. So that is one of the most dangerous, catastrophic events in construction, the breaking of a cable or the breaking of a rope. And you can see, and everyone was scared when everyone kept their proper distance when these small ropes were tested in the 2.5 million pound machine, because when they broke, they shook the building, they gave a loud bang, and I don't think there's a way of providing ductility in these wires, and that would allow a slow rupture like may occur in some other materials.
Yeah, we've been working on an exhibit that really features the worker stories, and it is every place you look at these wire, rope, and steel mills is danger. This sounds like one of the most dangerous areas, but
this is definitely one of the most, you don't want to get near it. You don't want to get near this experiment. I would say keep 10, 20, 30 feet away. And obviously, if they broke a rope on the pre-stretcher, it would have been catastrophic.
Okay, here's another question. If I understood correctly, Sunderland's post-tensioning method did not become the dominant style in pre-stressed concrete for bridge construction. What method was widely accepted, and why not Sunderland's?
He is right. The method that became dominant was the method that was so-called pre-stressing, meaning that you stretch the ropes, pour the concrete, and then let the concrete harden around the rope, and then cut the rope and let the rope try to shrink. And when the rope tries to shrink, it pre-stresses the concrete. My own judgment is this was a tragic direction that we took. The reason that we took this direction was that it allowed for manufacturing of products. So the post-tension product is something that is ad hoc, meaning that you design it for this one specific usage. Whereas you could pre-manufacture pieces of pre-stressed concrete, cut them to size, ship them to the site, and erect them. So I think it was the ease of construction and ease of prefabrication of a product that caused the American pre-stressed concrete industry to go into the pre-stressing direction rather than post-tensioning direction. But trust me, if this bridge was designed today, it would be considered state of the art, because that's the direction that people are going in. They're going into post-tension with open tendons. So for very large bridges especially, almost all of them have been built with post-tensioned open cables or open strands for inspection and corrosion protection. So I guess to reiterate, the direction that we took was based on ease of production, ease of making individual parts that could be shipped to the site and then erected on site. But in terms of modern large-scale construction, this is the direction that Sunderland defined, and this is the direction that is currently being taken for very large projects. If you're interested, one of the large projects that this is the Confederation Bridge between the provinces of New Brunswick and Prince Edward Island. This was all constructed using post-tension construction with open ducts. But again,
That's really interesting. Yeah, sorry, I was muted. I was talking, but you couldn't hear me.
No, but
Continue
this,
if you have
this
something.
bridge, if it were built now in Philadelphia at the same spot, would be considered state of the art. The design, this is a personal opinion, so don't quote me on it. The design that they chose was a regressive European design that really did not perform very well. They had to replace the Walnut Lane Bridge in the 1980s because of corrosion. So it was really not a progressive design. And I really meant it when I said that Sunderland's design was too advanced. The city of Philadelphia did not accept this too advanced American design versus European traditional design.
Okay, well, it's 6:59. We're gonna do one more question, and I think this is a good one. Did they pre-stretch suspender ropes on the Brooklyn Bridge, or how did they account for the stretch during that era? Pre-stretcher machine.
No, they did not pre-stretch it because they did not have the machine. I would guess, and I don't know the fact, is that they measured them by trial and error, or they used adjustable turnbuckles to attach to the hangers or the suspenders themselves in order to properly suspend the deck. So they either use trial and error, or they use adjustable turnbuckles to adjust the length, which they didn't know exactly when they attached the deck.
Well, this has been fantastic, Dario. Thank you so much. We're getting a lot of people in the chat saying that you are wonderful and that they're going to rewatch the YouTube. So
Okay.
typically after the presentation, we do email the link so that you guys can share it with people that you know. And I do want to say really quickly to you, Dario, that one of our board members has been sending me messages that we have an oral history from someone who worked with the pre-stretcher machine. So remind me if I don't email you that you
Yes,
should listen to that.
I would be extremely interested, and
Yes.
I want you listeners to contribute to the Roebling Museum. So get your
Woo!
contributions in, listeners.
I agree. So thanks everybody.
Thank you.
And we'll be emailing around the link if you guys want to watch again or share it with anyone that you know. So thanks again for signing up tonight, and we hope to see you at the next Roebling road trip.
Thank you.
Bye.
Bye.